Good morning, everyone. Welcome to Software Engineering. I'm Zhang Shuang from Software College, Northeastern University. From this lecture, we are going to learn Chapter 4, Introduction to Object. So far, we have learned computer languages such as Java and C++. And we know that they are object-oriented computer languages. So, surely you have understand object-oriented programming. Okay. Well, that's not enough for object-oriented software engineering. That means we still need to depend the concept of object-oriented paradigm to make us to do object-oriented analysis and object-oriented design better. Okay, the first point that we are going to learn in this chapter is coherent. Okay, let's learn the concept of module first. What's a module? Okay. A module is a lexically contiguous sequence of program statements bounded by boundary elements with an aggregate identifier. So that means a function in C language, for example, it can be called a module. And a class in a Java program or a method, all of these can be taken as modules. Well, before we discuss about the design of software, let's take the analog of the design of computer. For example, a great architect designs 3 silicon chips of a computer in this way. So there's a chip of register and another chip for ALU and one more chip for shifter. We know that this design is very good, and surely the current computer is really in this way. Well, a highly incompetent computer architect decided to design with 1 gate type per chip. So the design will be in this way. Chip 1. All the AND gates are in this chip, and all the OR gates in one more chip, and all the NOT gates. What do you think about this design? Even though these 2 designs are functionally equivalent, of course the second design is hard to understand, hard to locate files, and difficult to extend or enhance. And surely it cannot be reused in another product. So from this example, we understand that the modules must be like the first design. Okay? That means maximum relationships within modules and minimal relationships between modules. Usually, we'll just break up a product into modules for maximal interaction within module and maximal interaction between modules. So we get 2 more concepts. Module coherent. Coherent means the degree of interaction within a module. And another concept is module coupling. That is the degree of interaction between modules. So in structured design, a module is just its function. For example, a module computes square roots of a double precision integers using Newton's algorithm, and then the module is named compute square root, right? So it's just a function. Usually we name a function with a meaningful name. That means from the function name, you will know what the function is supposed to do. Okay, coherent. Let's learn coherent in detail. Coherent is the degree of interaction within a module. And what degree is the interaction within the module? There are 7 categories or levels of coherence. Level 1, coincidental coherence. Level 2, logical coherence. Level 3, temporal coherence. And then level 4, procedural coherence. Level 5, Communicational Coherence, and Level 6, Functional Coherence. The Level 7, Informational Coherence. And actually, Level 1 and 2 and 3 are bad. This from bad to good, from the worst to the best. Okay, so let's learn the coherence one by one. Okay. First, coincidental coherence. A module has coincidental coherence if it performs multiple completed unrelated actions. Well, sometimes some programmers think that every module will consist of between 35 to 50 statements. So, for example, he found that in Module A, Module B, and Module C, there's such a sequence of statements. We can see that the statements has nothing to do with each other. But this part appears in the 3 modules. So the programmers think it will be a good idea to construct this part of programs into one more module, call it M. And the module A, B, and C just call the module M. But the problem is that this degrades maintainability, and the modules are not reusable because this module are doing more than one task. Well, actually, it is quite easy to fix it. Just break the module into separate modules and each performing one task. Well, this coincidental coherence. Actually, we should try to avoid such kind of coherence. It is the worst. Second, logical coherence. A module has logical coherence when it performs a series of related actions, one of which is selected by the calling module. Example, Module A will call Module E, and Module B calls Module F, Module C calls Module G. Module E, F, and G are logically similar. They are composed into new module E, F, G. So this programmer just achieved a new module EFG, and inside EFG it will be like this. Since EFG are quite similar with each other, and surely they have some common codes, but they also have something different. So that means if module A is calling the module, and it should do something special for module A. If it is called by B, and then it should do something for module B. And the same with C. So you can see that actually the interface between the caller module and the calling module will be very difficult to understand. And surely it will be difficult to modify because it is really hard to read it. And the code for more than one action may be intervened. You see that the things are intervened. Okay? And the business flow of module EFG is controlled by the calling module ABC. Then this means this will increase the coupling between the caller module and the calling module. We must admit that this will be very low efficient. So logical coherence is really bad. We should try to avoid it. Level 3, temporal coherence. A module has temporal coherence when it performs a series of actions related in time. That means the actions in the module must execute in the same time. Okay. For example, initialization module, error handling module, or system termination module. Let's think about our own C code. Usually, we define or declare variables at the beginning of our program, right? int, abc, right? Try x, y, z, and so on, right? Okay. So surely the declaration of the variables has nothing to do with each other. But they are put together because all of them are for one objective, initialization. So this module for initialization is temporal coherent. Let's think about the error handling in Java program, for example. What do we do in the error handling block? For example, maybe we'll have to close some fields, or maybe we should process some data before the end of the part of code, right? But all of these things really has nothing to do with each other. They are together because all of them are for error handling, and it should happen at the same time. So we find that the actions of this module are weakly related to one another, but strongly related to actions in other modules. It is not reusable. Surely we have never heard about reusable initialization module or error handling module and so on, right? The fourth, procedural coherence. A module has procedural coherence if it performs a series of actions related by the procedure to be followed by purpose product. For example, this is the case for Gauss elimination algorithm. You can see that there are more than one tasks inside this module, but all those tasks should be executed in sequence. So that's why it is called procedural coherence. Well, the actions are still weakly connected, so the module is not reusable. It still has problems. Level 5, communicational coherence. A module has communicational coherence if it performs a series of actions related by the procedure to be followed by the product, but in addition, all the actions operate on the same input or output data. For example, here's the example of communication coherence. This is a module, and it has two tasks. One is to generate a salary table, and the other is to calculate average salary. Well, the reason that they are within the same module is because they have the same input data. And surely the output are different. The output of general salary table is to get salary table. And surely this is to give out the average salary. And surely such kind of module still lacks of reusability because it will execute more than one tasks. So level 6, functional coherence. Module with functional coherence performs exactly one action. Just now in the previous 5 levels of coherence, we have seen that such kind of modules perform more than one actions, more than one task. And then it will get many problems. And the only solution is try to get each module to execute only one action, right? So why is functional coherence good? Functional coherence will lead to more reusable. and make corrective maintenance easier. Because the module executes only one function and it is much easier to do fault isolation, and it will cause fewer regression faults, and it is easier to extend product. So that means for structured design and programming, functional coherence is the best that can be achieved. Well, one more coherence. Informational coherence. A module has informational coherence if it performs a number of actions, each with its own entry point with independent code for each action, and all performed on the same data structure. So what is it? This is a module, and this module has more than one task. For example, this is initialize sales region table, and another task is to update sales region table, and the third is print sales region table. And we see that each action has its own entry point and its own exit point. Okay, that means it has its own output. All these actions operate on the same data structure. Okay, here is the data definition of sales region table. So this is informational coherence. And this is just an abstract data type. We can call it an abstract data type. Maybe you think this is quite familiar with us. Well, it is. It is really something like the class in object-oriented programming. And actually, we'll continue discussing with this issue in later lectures. Well, okay, so much for coherence. Thank you.